Hi. Today we will continue with Math476 online lecture 2. Okay. Today we will talk about the operations with ideals. It is the chapter section 2.8 in the book, operations with ideals. So as usual, let R be a commutative ring. Ring with identity. So in general, this will be the pure ring of polynomials in general. So let I and the J be ideals in R. Let's write like that. Ideals in ideals. And so here is a definition. So before the definition, let's consider this product A times B such that A is in I, B is in J. So if you consider this product, in general, this is not an ideal. In general, this is not an ideal, but we can look at the ideal generated by the set, and we will say that this is the product of I and J. Okay. So if so for an ideal I, we define for an ideal I1 IN, does this product is the ideal generated by the product of n elements such that AI is in II. So you multiply the elements of I1 through IN, and then look at the ideal inside R, of course, inside R generated by these elements. So in general, this IN is not equal to the ideal generated by AN such that A is in I. So rather than that, it is in fact IN, named I times I times I, is it is the ideal generated by A1 AN such that these AIs are in the same I. So okay, let's see. So that if we let's set I to the 0 to be R, then this ideal I is inside this one. I square is contained in I, and I cube is contained in I squared, etc. IN, it goes like that. So here's an example. So let's take R to be the ring of polynomials over the field is K, over the field K. Let's take I to be the ideal generated by X1, X2, and XR. Then this I to the N is the ideal generated by monomials. Monomials of degree N. The reason for this is that here is the reason for this. One can show it easily that if you take if I is generated by some S and J is generated by, let's say, some ST, then instead of taking the all integer as a generating set, instead of taking the all elements from product of from I and J, you can only consider the product of S and T, where S is in S, T is in T. So if you consider this product and look at the ideal generated by them, that's equal to the product of the ideals I and J. This is easy to show. Okay, so that this okay, let's oops, not this. This is not R. So R will be something else. So let R is now R is let's take R to be this polynomials x1, xn generated xr, not x, xr generated divided by I to the n. Then this is a vector space over K. R is a vector space over K, over the field K, and its basis the base of it is that x1 that xr to the I1 IR, oops, not IR, such that the left cosets of this, let me write like that, such that this the sum of I1 IR is less than n. So let me give one example. An easy case. Let's take K to be in two variables, x, y, and in this case, let's take I to be again x, y, then K x, y over I to the n is, let's take n to be 2, for example, and I to be 2. If we take any polynomial, any element in the set and any left coset, f plus I not I2, this is I squared, f plus I squared. This is this can be written as, you can check this as that any element can be written in this form: 1 plus I squared plus x plus I squared plus y plus I squared. So the linear combination of these, so that it is lambda 0, lambda 1, so lambda 2. So the reason is that okay, so this is so that this is a basis, this one bar, namely this class, class of 1, and x1 bar, y1 bar, sorry, is a basis of R. So okay, now if I is an ideal, of R, and R is a subring of S, of a ring S, then I is a subset of S, so that we can look at the ideal generated by I in S. So the ideal generated by ideal in S, generated by the elements of I is IS. This denoted by IS like that. So one, you can check that. You can check that IS to the N and I to the NS are the same thing. So for the product, it is like this, but for the addition of ideals, it is easier. So addition of ideals, or sum of ideals, or sum of ideals, let's say. Sum is easier, better. Sum of ideals. So let I and J be two ideals in R. So you can check that if you take an element from I and take an element from J, add them up, so that you look at all these sums. I is in I, J, B is in J. If you look at all these sums, this is an ideal. Unlike the product of elements, this is an ideal, and it is called the sum of these ideals. And this ideal I plus J is the smallest ideal containing I and J. So why is that? So definitely, you see, the first thing is that you may check that I plus J is an ideal. And clearly I is in I plus J, and J is in I plus J. So these are easy to show. And now let K be an ideal with I is in K and J is in K. Let's show that this I plus J is, let's show that I plus J is in K. So that we claim, so that this I plus J is the smallest ideal containing I and J. So let's see, let's take an element, let X be an element from I plus J, so that we can write X as A plus B, where A is in I and B is in J, so that A and B are in K. So hence X is equal to A plus B is in K. So that means, therefore, I plus J is inside K. So that means I plus J is the smallest ideal containing I and J. Or if you like, this is, or another way of writing this, or equivalently, I plus J is the intersection of all ideals K, such that K contains I union J. K contains I, K contains J, and K is an ideal, of course, in R. Okay, that's the smallest ideal containing R and J. Okay, here's the definition. We say that the ideals I, J in R are comaximal if their sum is equal to the identity, is the whole R. Namely, you can write one as the sum of two elements from I plus sum of two elements A, B, where A is in I, B is in J. So if you can write one as like that, so if I plus J is equal to R, so you can write one like that as A plus B. If one is in A plus B, then that means one is in I plus J, so that I plus J is equal to R. So that comaximal is I and J are comaximal if and only if you can write one as the product sum of two elements from A and I and J. Okay, here's an lemma. The first lemma property is that this I, suppose I and J are ideals in a ring, then I times J is always inside I intersection J. And the second is that, if I and J are comaximal, then I times J is equal to I intersection J. Okay. And let me say one more thing, which I will not prove. I will leave this to you. If I and J are maximal ideals, ideals in R, and if I is not equal to J, then I plus J is equal to R. I will leave this to you as an exercise. You can show it easily. Okay, here's a proof. Okay, so I plus J is, remember, if the first one is I plus J is inside I. The reason is that if you take any generating element, so let A times B be an element of generating set of ij. So if this is an element, so since A is in I, so A times B is in, and since I is an ideal, A times B is in I, so therefore I times J is inside I. And similarly, I plus J is inside J, so therefore I times J is contained in the intersection of I and J. So intersection of I and J is an ideal, of course. And second, the proof of the second statement is as follows. So suppose I and J are co-maximal. Suppose I and J are co-maximal. So, and we will show that I intersection J is inside I times J, right? Okay, since they are co-maximal, I and J are co-maximal, we can write one as the sum of two elements where A is in I, B is in J. We can write like that. Now, so let X be an element in I cross, both in I and J. Then we can write this X as X times 1, which is X times A plus B, or it is X times A plus X times B. Now, A is in I, this is in I, that's in J, so that this is in IJ, in the product, and this is in I, X is in I, B is in J, so that this product is in the product IJ, so that the sum of these two elements is inside IJ. So that means, therefore, this intersection, I intersection J, is inside I times J. So this is the other part, so that this is proved.